Okay, so the linear impulse momentum equation goes the integral of forces. Let's write sum of the forces over time dt equals m times v2 minus v1. And those are all vectors. That's a linear impulse momentum equation. And for that equation, if the left-hand side, the sum of forces goes to 0, then we will end up with the conservation of momentum, linear momentum. That's something we talked about in section 4C. And so now what is this angular momentum, angular impulse? How can we find angular momentum? Recall what we use. We usually use movement to find angular momentum. So recall what you learned in statics. What is movement? Let's call this movement. Let's see, the movement is about a fixed point O. So what's the equation for movement? If we have, let's call this fixed point O, then we have a force somewhere, let's call this F, and maybe there's a force is applied on a particle or something. And if we know the distance from O to that particle, let's call that distance of position vector R. Let's call this point particle P. And we know this position vector is called Vp/O. And we know the force. And how would you express movement about the fixed point O from this force? From what we learned in statics, that goes like this. The movement about a fixed point O equals the position vector from that point, start from point O, pointing to point P, which is Rp/O, cross product, and the force vector. So that's what we learn in statics for the definition of movement. And since in this chapter we're talking about kinetics, so we can rewrite this F in terms of Newton's law, right? F equals ma. So let's do that. Equals ma. Keep in mind that I'm doing everything in vector form. Mass doesn't have direction, but I do make sure I have the arrow on top of acceleration. And as we know, acceleration can be written as the first order derivative of velocity with respect to time, right? So we can keep write this as Rp/O cross product m times dvp. That's the velocity of the particle dt. So we can keep simplify changing the plain math tricks to get something what we need. So this term, this something cross something's first derivative with respect to time, and can be written as d dt times Rp/O cos m Vp minus d Rpo/dt cos m Vp. Okay, maybe you're a little bit overwhelmed. Like, how do we just jump from this step to all the way to here? So this is a trick. It's magic. And it's if you have a vector A cross, let's use a different color. Let's just set note. So if you have a vector A that cross with a first order derivative with respect to time with vector B, and this whole thing can be rewritten as dA cross B dt minus dA over dt times cos B. So this is just a side note. That's how we change from this step to this step. Okay, and if you look what we have so far and just leave the first term alone, look at the second term here. What is dr p slash o over dt? So this r p slash o, that's a position vector. It's a kind of distance, right? So you take the first derivative of distance with respect to time. What is that? That is actually, it will give you speed, right? Velocity. So you realize that is actually this velocity of particle P. So what you end up with here is you have Vp from this term here, cos mVp. M here is a constant. So pretty much this is the Vp cross product itself. So you know if something cross product with itself and the product is 0. So this whole second term goes to 0. Then what we left here, it's that we left with only the first term, which is O equals d dt rp slash O cos Vp. And this is the only thing we left. We get a new expression here. And if we can redefine, like just define, we use the letter H, capital H, O. Use that to kind of replace what is inside of the parentheses. That is rp slash O cos mVp. So this is what's inside of parentheses. So if we just manually define HO is equals to that, then we can actually write our movement in terms of something similar, simpler, easier to look at. So dH dt. And let me highlight this. So this HO vector here, that's what we call, this is angular momentum. And compare this with what we learned in linear momentum. If we go back here, linear momentum is just mass times velocity, right? That's a linear impulse momentum equation. But in this section, the angular momentum, it's a cross product between R and mVp. They're both vectors. Okay, and then we end up with this, which is a simpler expression for movement. We can keep this since we have d something over dt on one side of the equation. We can actually throw this dt term to the other side. Like now we end up with m dt equals dho. And we can take the integral on both sides of the equation. And can take the integral in terms of this from time 1 to time 2. And The other set of equation, this dt, integral dho, since there's nothing here, so that can be just written as ho2 minus ho1. That's angular momentum at time 2 minus angular momentum at time 1. And we can just copy this side. Okay, and this would be our angular impulse momentum equation. So on the left-hand equation, similar with what we learned in linear impulse, that's the angular impulse. On the right hand of equation, that's a change of the angular momentum. It's pretty similar with what we learned in linear impulse momentum equation. And we can express this, let's write this. This is called angular impulse angular momentum. Equation. This equation, actually not, it's the angular momentum h here can be expressed in different coordinate systems. So someone asking test exam questions, I will answer that at the end of class. We're going to have 45 minutes to explain all the exams. Okay, so in Cartesian, let's change color here. In Cartesian coordinate system, and our h, the angular momentum, can be written as, we know the definition is r cos vp, right? This, if everything is in Cartesian coordinate system, then there will be mass, that's a constant, doesn't change, times the expression for position vector in Cartesian form, that's gonna be x components I direction plus y components, the distance on y on j direction, cos, and we have this velocity terms, which is a vector. If we want to read that in terms of Cartesian coordinate system, that would be vector, the velocity component on x direction, which is I, plus the velocity component on y direction, that's j. And if you break this cross product and do the calculation, and this will end up with mass times xp vpy minus yp vpx. That's just a regular product in between distance and velocity components. And this whole thing, since this cross product is on k direction, so this is a vector. Remember, we're doing the angular momentum, that's a vector. And the angular momentum is on k direction. So if we draw this in 3D, it's kind of our j, I, and our k would be on that direction if you use right-hand rule. Okay, and so this is the expression for angular momentum in Cartesian coordinate system, right? And then we can write the angular momentum in your favorite coordinate system, that is polar coordinate system. Okay, if think about how could we write this angular momentum in polar coordinate system. So angular momentum, from the definition we know, is rp/o equals mvp. If we express everything in polar coordinate system, and this r vector, which is position vector, can be written as r on ER direction. Remember, in polar coordinate system, we only have ER and E theta, and that can be crossed with you can write this Vp, the velocity in polar coordinate system. Remember, that's something r dot something theta dot, right? So it's r dot on ER direction plus r theta dot E theta direction. That's just the velocity expression for velocity under polar coordinate system. Don't forget we have that mass, which is a constant. You can just write that in the front. Okay, then you can break this down, and you end up with this angular momentum in terms of polar coordinate system equals mass times r squared and times theta dot on k direction. Okay, so this is expression for angular momentum in polar coordinate system. And you realize the expression has mass times distance, which is the distance from the fixed point to the particle, distance squared, and times theta dot. What is theta dot here? Theta is an angle, and we take a dot for the angle. That's the angular velocity. That's omega, right? And this vector is on k direction. So we have these two expressions of angular momentum in different coordinate systems. Okay. So like what we did here, we show you IJK. That's kind of like 3D. If our particle is moving on the INJ plane, and you will realize that our angular momentum h is only on k direction, right? K. So the angular momentum is perpendicular to the plane of motion. Angular momentum is perpendicular oops, that's a hard word to spell. Perpendicular to the motion, to the plane of motion. That unit vector k tells you that information. Sorry about the bad handwriting. Okay, then now I have a question I want to ask you to make you think. So what's the first question is, so under what condition angular momentum will be conserved? So I want you to think about under what condition, let's go back here, the linear impulse momentum is conserved. And we talked about that multiple times. This only under the sum of the forces equal to 0, then we can see the linear momentum is conserved. So same thing here. Let's go back to the angular impulse momentum equation. If we want to make the conservation of momentum, angular momentum hold, the only way to do that is to make sure the angular impulse, the moment is 0. Then we can see the conservation of angular momentum. Okay, so for this, only if sum of all the moment about the point equal to 0, then we can see we have conservation of angular momentum. Okay, and so what happens if sum of the moment about the fixed point is 0? Let's go back to the equation. If this moment goes to 0, then the left-hand side is 0. On the right-hand side, we're only left with HO2 minus HO1. Then that tells us under this conservation that we would have 0 equals HO2 minus HO1, the change of angular momentum. And we can, since we did this in polar coordinate systems, right? We can write HO in terms of polar coordinate system. So if we do that, plug in that, so m r squared, let's replace theta del with omega. Omega at time 2, that's omega 2 on k direction, minus r squared, let's call this r2, r1 squared, omega 1, okay. That equals to 0. And then this will give us something, information about how omega 1, omega 2 changes in terms of how you change the position R1 and R2. Oops, on the bottom, here should be 1. Omega 1 over omega 2 equals R1 squared over R2 squared. That's under a conclusion you can get under the conservation of angular momentum. Okay, then I have a follow-up question. Since here we talked about the conservation of angular momentum, that's under the condition when sum of all the moment is 0 about that fixed point. So under what condition would momentum equal to 0? So when would the momentum equal to 0? When you think about that, so from the definition, momentum equals R cos force vector, right? That's R cos product force vector. So in order to make the moment equal to 0, one thing we can do is we can either make R equal to 0 or make forces equal to 0, right? And if force is equal to 0, that's very simple, easy way to tell. But in most of the problems examples, we will have the forces, probably the sum of the forces are not equal to 0. However, this R, the distance from the force to the fixed point, is equal to 0. So what happens if the force, the vector R is 0? Let's draw this. If this is the fixed point O, and if the distance between the force and the fixed point is 0, that means your force is passing through the fixed point, right? So your force is passing through that point O. Under that case, we call those type of force are central force. So the central force does not contribute to movement or angular momentum. Sorry, doesn't contribute to movement impulse. So then if you have forces, only have forces pass through this fixed point, then it would be safe to say the movement equal to 0, then you have conservation of angular momentum. Okay, and So in other cases, the force can either like towards the fixed point, or it can go all other direction. It can either be away from the point. So you'll get the same conclusion. No matter it's towards to the point of getting away from the point, and they're all passing through the point. And you can always see there's conservation of angular momentum under that case. Okay, any questions? Those are the kind of the concept how we get into the angular momentum all the way from, we started from the linear impulse momentum. Okay, if we don't have any questions, we can move on to some key characters of angular impulse momentum equation. So the angular impulse momentum equation, you will also see that probably is written in different order. You can put the angular momentum at time 2 on one side of equation and through everything else on to the other side of equation. Plus that HO2 can be written equals to HO1 plus integral m dt. And make sure you have that, I'll highlight this. Make sure you have that O. Oops, I'm missing this here. Make sure you have that O here. It's important. Since we're talking about angular momentum. The angular momentum and movement has to be about a point. So that highlights there, it's a point O, that's a fixed point we're talking about. So whenever you use angular impulse momentum equation, first identify which point you're referring to. Okay, next thing. Always kind of compare this with the linear impulse momentum equation, right? Since it's pretty similar. In the linear impulse momentum equation, we have the linear momentum as m times just velocity at time 2 can be written as mv1 plus integral 1 to 2 forces dt, right? You compare this to the third thing is and remember the central force we're talking about. Those are the forces that passing through that fixed point and generates zero movement, generates no movement. And that tells you delta H equals 0. That is, change of angular momentum is 0 if you have central force. And let's see what other things. And also we mentioned a conclusion under conservation of momentum. And we will get a relationship between omega 1, omega 2, right? So that would be an important conclusion. Equals R, sure, R1 squared. Oops. And I think I made a mistake here. So, sorry, I made a mistake here. The subscript is not right. So it's omega 2 on the top, omega 1 on the bottom. And on the others, yep. So it's opposite flipped. So on the left-hand equation, you have omega 2 over omega 1, but on the right-hand equation, you have R1 over R2 squared. Let's change that. Omega 2, omega 1, R1, R2 square. That's only under the conservation of angular momentum, delta H equal to 0. Okay. And another very important conclusion from the angular momentum and angular impulse equation is this equation only tells us the velocity component on radial direction. If we're looking at, go back to the Cartesian and polar coordinate system, if you look at what we did in polar coordinate system, you realize that we can end up with something with a theta dot inside, right? So theta, if you look at theta dot inside of the velocity expression under polar, it's only appears appearing under e theta direction. So that means this angular momentum equation does not tell you anything about r dot. So if you use angular momentum equation, you only find information about velocity on radial direction. Only find radial components of velocity. That is r theta dot on e theta direction. And if you want to find anything about r dot, which is on e hat r direction, then you will need to use work energy equation. Okay. Okay. Those are the things I think you should need to pay attention in this section: angular momentum, angular impulse, right? And if you haven't get a chance to write everything down, don't worry, all the videos will be posted on YouTube channel. Okay, now we spent a lot of time to go through all the concepts. Let's look at an example in this section. So let's look at example 4D1. So in this example, this is top view. So imagine you have a table. On the edge of the table, there's an arm or guide. And the particle, it can slide on this guide. Its arm is called particle P. With smooth. This is a smooth arm, and the table itself, it's smooth, though there's no friction. We know the initial distance from, let's call this point O to P. It's R. And so this bar, this arm can rotate on the tabletop, and this particle P can sliding on the guide on this arm with no friction. So in this problem, we're given the weight of the particle P was 2 pounds. And we know the omega 1, how fast this arm is rotating. That is 20 rad per second. We know the distance, let's call this R1. R1 equals 3 inches. And we need to find out what is the velocity, the angular velocity. That's the omega 2. When this particle is at a new position, let's call this R2. That's the distance from the particle to the fixed point O, equals 224 inches. Okay, if we have a problem like this, how can we use angular momentum, angular impulse equation to do this problem. First, we always want to have kind of free body diagram to see what are the forces we have. So in this case, since we both have bar is rotating, it has a motion itself, the bar is rotating on the tabletop, and this particle and can slide along that bar, the arm. So both the particle and the arm, they're kind of assistant. So we want to have a free body diagram for the system first. Let's have this arm now with that particle, and that's our point O is over there. If you look at this system, what are the forces? Since here this is a top view, right? So we're looking from top to bottom and top down. There will be no gravitational force and normal force, right? But if you look at that point O is fixed there, then from what you learn in statics, even we're in dynamics, but you know there's some reaction force there. So we can call that Ry. And Rx, some reaction force pointing to the point O. Okay, then that's it. That's all the forces you can find on our free body diagram. And like we mentioned, first we want to say if the angular momentum is conserved. Right? From the equations we have, if the angular momentum is conserved, we can find some very useful informations, right? You can simplify our equation. So first we want to see if this term is 0. Then we learn if there's a central force, there will be no moment, then we can see the conservation of angular momentum. And if we go back to this example, and the only two forces we have, Rx, Ry, are pointing into that point, fixed point O. So that's important information that tells us the moment is 0, about point O. Right? Those are the central forces. And if that is the case, we have conservation of angular momentum. Okay, then we can start writing the equation. That is the angular momentum, HO1 equals HO2. Right, we learned HO1, HO2 can be expressed under polar coordinate system. So that can be written as m, the mass of the particle, times r1, position 1 square, omega 1 equals m r2 square, omega 2. And we can find out the angular velocity at position 2, since this is what we're trying to find here. What's the angular velocity at this new position when r2 equals 24 inches? So we can write expression for omega 2. Omega 2 can be written as r1 square over r2 square times omega 1, right? And you can plug in all the numbers, plug in what is r, r1, r2. R1 at the beginning, it's 3 inches, R2 is 24, and omega is 20. So you have 24, I forgot the number, 3 square times omega 1, which is 20. And you're able to find out what is the angular velocity at this new position, which is 0.3125 radian per second. Okay, so that's a simple example to show you how to apply the angular momentum equation, how to identify zero movement so you can have conservation of angular momentum. Right. Okay, and so we won't go very deep in section 4D, and even if they will be in the exam, it would be only about concept instead of solving a problem. Just this information would be good for you to have for the next chapter. Would make more sense in the next chapter. Okay, I've got another question here. That is, Cohen's asking, what about the weight of the particle? Would that affect the free body diagram? Okay, so Cohen is asking for why I don't have the weight force on our free body diagram. So this problem, the setup of the problem is we're looking at this is top view. This is a horizontal plane. So this particle is sitting on the tabletop. We're looking from top down, if that makes sense. And also we're drawing the free body diagram from top down. So your gravitational force will go into the screen, if that makes sense. That's why on the free body diagram here, we only have the reaction forces acting at point O. Okay, thanks for that question.
Dr. L?
Yes?
Will you look at Lucas's question in the chat?
Okay, so that's a question on exams, right? All right, if we don't have any questions on section 40, then I'm going to use the rest of time to talk about the exam. Okay, so the exam will the test on Monday be open all day or during the class time? Okay, that's something I'm about to talking about. So the exam on Monday will be during our class time. Let me turn off our video